Hope you had a good break, yeah? I think it's long, 1.5 hours is too much. So maybe in the next one, like our whole session is 1.5 hours, right? Maybe after 40 minutes something we can have 5 minutes break, yeah? Just so it goes in a relaxed way. Okay, so this was the question we did put before we stopped. Can you think of other methods and controls than frequency scaling to stop the thermal cover channel? Yeah. So I think this one we have discussed. Anything else? What you could think? If not a problem. We are going to cover those things anyway. Yeah. Okay. So let's go to the slide. So one of the method we have developed in our group, and we say it is selective noise based countermeasure. Yeah. So you may think like this is some sort of noise that should be added into the system. Yeah. So you remember, like the main aim was, if there is a temperature profile that is up and down, we want to make it as flat as possible. Yeah. And by doing dynamic voltage frequency scaling, we could achieve that. Yeah. But now you can also think of from a software point of view. Yeah. So you can take a program, that program is not doing anything useful. Yeah. That is why we say it is a noise. Yeah. But you have to select it carefully. Yeah. So that program should not be very light or should not be very heavy. Yeah. So now when temperature profile is again kind of going up and down, and the information is deduced from that, again like I said, main aim is to make this profile as flat as possible. Yeah. So now with this extra program, you can think of using a chip a lot, so you can increase the temperature. Yeah. And at certain points you can remove this program from the processor. So in a way, from a software point of view, it can help you. Yeah. Like in my laptop, right? Sometimes you can run a lot of programs, then temperature increase, and sometimes you don't need to run. Yeah. So let's look into this a bit. So this one is like, typically you remember we said thermal signal can be like this. Yeah. There is a change in the temperature, change in the temperature, change in the temperature, change in the temperature. So this is all bit 1. Yeah. If your thermal signal is like that, from the transmitter or at the receiver, you will know like this is all bit 1. Yeah, easy to get. Now like I said, what's the aim? Making this as flat as possible. Yeah. So what you can do, when at the transmitter there is a program that is doing this kind of profile, right? So you can add some extra program or extra noise. So when your temperature goes up, yeah, when it starts coming down, you can start that program. So then this temperature will stay the same. Yeah. When again it starts coming down, and when you add, basically you have to also remove at the right time. Yeah. When it again starts coming down, try to add that extra noise. So you may end up getting some profile like this. Yeah. So you can see here now, although this temperature is received at the receiver, but receiver will not get any useful information. So you can say that the bit error rate will be very, very high. Okay. So this is just finding a carefully crafted program that does nothing useful, but just disturbs the temperature in a way that makes the information useless for the attacker. Okay. Again in this one, like detection can be done in the same way. Yeah. And the defense, like I said, is considering bit 1 represents change in the thermal signal, like going up to down, and bit 0 represents like no change. Yeah. No change in the signal, same like previous one. Yeah. So here, like I said, if bit is 1, yeah, that means it's change. You can add extra noise to heat the processor, so it will keep the temperature higher, so it's not going down. So attacker is confused basically. Yeah. So this is typical software way to do it. And this is the results of this adding this carefully crafted noise. So if you see the temperature signal, yeah, and this is over time. So this one is basically without any noise added, yeah, normal temperature profile, from which attacker is able to get useful information, yeah. Now again, you remember, like I said, temperature goes up, it starts coming down. At this point, you initiate your extra noise. So temperature will not come that down, maybe little bit down. Again, whenever it tries to come down, you initiate this program. So you will see like more flat profile, okay. So from this one, it's not easy to get the useful information, yeah. So this is like example of one of the experiments, how the results look like, okay. Now this is the result comparison with the DVFS approach. So we saw the DVFS approach, right? You change the frequencies. So this is 4x4 system. So here you can see like the selective noise based has more higher bit error rate, yeah, than the DVFS approach. So the situations basically we considered, these two systems, the selective noise based approach is getting better results, yeah, which simply means it is trying to make the temperature more flat in comparison to the DVFS approach, okay. So there's more detail in this paper. If you want later on, you can look, but with this one I just wanted to give you an idea, like one way is you use hardware controls, but another way is you can use some extra softwares to flatten the temperature, okay. Okay, so now I have a question. So we did DVFS, yeah, and we did noise addition. So can you think of any further ideas? Again, what you want to do, you may want to make the temperature as flat as possible, yeah. Can you think of there is any other way to make it as flat as possible? So we have seen one hardware control, one software way, yeah. Anything else you can think of? Let me put that screen, yeah. So okay, hopefully you will see the screen, yeah, on your phone. No? Okay, before we go next, let me try to give you some example. Yeah, this kind of noise addition is very powerful. I don't know if you have heard about this Malaysian airline, yeah, that got disappeared. So there is a documentary on it. So there is a theory like how it got disappeared. So it said like this was going from to China, right? I think from Singapore or somewhere in Malaysia. So the documentary said it basically had some kind of defense equipment or something, and US didn't want it to reach there. So you know, like these airplanes, they are always communicating at certain frequencies, that with the radar to the base station or all the basically traffic controllers, yeah. So you know, like if it is communicating at certain frequency, so one way to stop that communication is you put a lot of noise at the same frequency, right? Then it's kind of you're jamming everything. It's like too many requests, then it can't get. So that documentary says there were like two fighter jets near to this airplane, and they jammed its communication from all the places, and then they kind of hijacked and then took it somewhere. Yeah, this is just a theory. I don't know how much true it is, because that airplane is never found, yeah. And some people say they found some debris or something in Africa, but it's all theories, yeah. So you can think like noise addition is kind of in a way to stop the attack, but it can be also used to let the system down, yeah. If there is some communication happening at certain frequency, just jam that channel. Yeah. Okay. Okay, so use of gray codes for encoding. I think that's possible. Yeah. You need to think a little bit. Okay. Yeah, so I think it's about basically confusing the attacker, right? You use some kind of coding to basically confuse the reviewer, confuse the attacker. Yeah. So could be possible, but need to think more how exactly this can be done. Okay. Okay. So we have seen selective noise, its results. Okay. Sorry. You know, in lots of systems there is a fan, right? These days it's not, but there is another control, another mechanism to control the temperature, right? You know, in this kind of systems, there is a fan. When the temperature becomes very high, it turns on. If it keeps increasing, the speed of the fan keeps increasing. So you can say this is another control that can control the temperature. Yeah. So because it can control the temperature, so you can use the fan speed as well to do the countermeasure. Yeah. Again, run the fan at appropriate speed at appropriate time so that your temperature profile is as flat as possible. Okay. So one of my PhD students did this work. Let's look how little bit details how exactly it works. Okay. So what it does, it looks two things. So one is like T recorded, so it's like the temperature at the previous instance. Yeah. And one is temperature current. So what is the temperature now? What is the temperature previously? Yeah. So this is what we want to know, right? You see, like temperature goes up to down. So if it's high at current, previously it's low, that means there's an information. Yeah. So if it is different, yeah, so basically that's not equal. Yeah. If it's equal, that means there's no information. Yeah. So then you check if the current one is higher than the previous one. Okay. If that is true, so basically you kind of check some range. Yeah. In what range the now it is, and in what range the previous one it is. So we define some range, and if that's the case, basically you increase the fan speed. Yeah. So you see, like the current temperature is higher, right? Now it's higher than the previous. So what you have to do, basically you need to cool it down. Yeah. So you increase the fan speed. Okay. In other case, if it's other way around, if current one is less than the previous one, so basically you can decrease the fan speed to make it even higher. So what is the aim? We always want these two temperatures to be close to each other. Yeah. So that attacker cannot get anything. Yeah. So it's like if this one is higher, you increase the speed, so it cools down and reaches close to the previous temperature. Okay. Similarly this one, if this one is lower, you decrease the fan speed so the temperature can be increased to reach the previous level. Okay. So this is one way, fan speed, and this is the kind of, you know, some trial experiment. Yeah. Brute force approach, like my student took different range and find out what will be the appropriate fan speed for different range, so that the whole temperature can be made as flat as possible. Okay. So this is one way, and these are some results. Okay. So in this one now you can see it has been tried to look all the approaches together. Okay. So this thermal covered channel with DVFS, thermal covered channel with one extra noise. So it's like there is one simple program. Yeah. And then thermal covered channel with selective noise. So it's like that extra program is multiplied maybe 3 times, 4 times, but not 100 times. So that is like finding the appropriate level of noise. Okay. and this one is with controlling the fan speed, and there could be different range of the fan speed. Okay, and then here is TCC with DVFS and fan speed. So it's like we are applying both together. Okay, and then here we are applying selective noise and fan speed together, and at the end we are applying all the approach together. Yeah, DVFS, selective noise, and fan speed. So you can see what is the level of bit error rate. So here is 98%. Yeah, that means even though attacker is getting the information, it's only 2% of the information is useful for the attacker. So not very useful. Yeah. So this is the basically bit error rate, and we also basically logged the temperature. So you can see what's the temperature level and what is the average power consumption as well. Okay, so you can see here more or less when you apply all of them together, this is the best approach. Yeah, but here you have to decide like which one is applied first, which one is applied after that, if you are still not satisfied, like the temperature is not as flat as possible. Yeah, okay. So these are the, you can say, 3 controls in the processors that we can apply. DVFS is widely used in all the processors. Selective noise is just a software. Yeah, fan speed is something else that you can control. Okay, so and if you want to look more details, this is basically published in this conference, and all the experimental setup and everything is provided there. Okay. Okay. Can you think of other covert channels than temperature? I think we have covered this question. Yeah. You said there could be power. Yeah. There could be something else. There could be timing. Yeah. Or there could be sound. Yeah. So let's go to the next one. Yeah. So next one, timing covert channel. Yeah, like I said, sometimes the timing information can be used to transmit real information or sensitive information. So again, we have developed one approach. It's called IPD based covert channel. IPD stands for inter-packet delay. Yeah, so it's like you send a packet from one place to another. When it is receiving, so it's like how much is the delay between first packet, second packet, third packet, fourth packet. Okay, so we keep transmitting. Yeah, and then you calculate, like if your received inter-packet delay is greater than some threshold, you can say it's bit 1, but if it is less than the threshold, it's bit 0. Maybe it's not very clear, so let me try to show you with this example. Okay, so here you can see packets are being sent. Yeah, so packet 1 is received here, and packet 2 is received after 100 cycles. Yeah, packet 3 again after 10 cycles, and then packet 4 after 100 cycles. So this is how it keeps repeating. Yeah, now imagine at a transmitter that is sending something to the receiver, and if there is some sensitive information at the transmitter, yeah, you can send the packets in a manner like the first packet takes long time and then it will be received late, and the second packet is sent very fast. Yeah, so it is received in less time. Okay, so when it's taking long time, you can say there is a bit 1 stored into the transmitter side, and if it is taking less time, you can say it's bit 0. Yeah, so this is how you can basically use the timing information to get some sensitive information on the transmitter side. Yeah, or on the transmitter core. Okay, so here I would say I can set a threshold like 50 cycles, right? If my packets are received after 50 cycles, I will say bit 1. If it is less than 50 cycles, I will say bit 0. Yeah, as you can see, the timing is very, very useful. Yeah, and the timing attack is actually very popular. It has been done in lots of Intel processors as well. Yeah, so people have tried, like there is some program running, right, in a core. You take another program, you try to measure its time. Yeah, try another program, So depending upon the time that other program is taking, you can actually guess what exactly is running in the processor. Okay? Yeah. So this is just very simple example. Yeah. You can use inter-packet delay or inter-packet receiving time to get the real information from the transmitter side. Okay, any questions? It's clear? Easy, right? Yeah. Okay, so how it can be detected and how it can be stopped. Yeah. So again, if you remember the temperature one, right? If you want to stop it, you need to make the temperature as flat as possible. If you want to stop the timing one, you want this timing equally the same. Yeah. So all the packets should be received in the same delay. Yeah. The inter-packet delay should be the same, right? That's how you can stop. Yeah. Detection, we know it's easy. There could be this thresholding mechanism, like I said. Yeah. If it is received after 50 cycles, it's bit 1. If it is received in less than 50 cycles, it's bit 0. So that thresholding mechanism can be used for detecting, but stopping, you have to just make all these intervals the same. Yeah. So what you can do, basically, you can do some modulations. Yeah. So it's like when it's taking long time, you modulate in a way it takes the same time. Okay. So again, make the side channel information as flat as possible. Yeah. So nobody can get the information from it. Okay. So more details again is in this paper. This is a transaction paper in 2022. So you can look more there. Okay. Yeah. All right. Okay, the next one, inaudible sound covered channel. Yeah. So we saw the temperature, we saw the timing. Yeah. We can also see how the sound label can be used to get sensitive information. Yeah. And how it can be stopped. So, and this is also called an inaudible sound covered channel. Yeah. So it's like we cannot really hear. Yeah. The frequency range is quite different. So it's like, let's say in one of the phone you have some password stored, and then there could be inaudible sound covered channel. Yeah. So it's like sound level for bit 1, maybe it's high, sound level for bit 0 is low, but we cannot hear it. Yeah. And with that, if it reaches some other place, the information can be decoded. Yeah. So again, how you can stop it? The main thing is, again, like I said here, the sound label is high or low, right, for 1 and 0. So you need to make the sound label at the same level so it can be stopped. Yeah. So what you can do, basically you can have some kind of extra mechanisms to really see what is the sound label. Yeah. You need kind of a microphone, right, and that microphone will receive it, and now if it's kind of sensing there is high sound label, low sound label, those kind of things, then it can add some extra sound just to make the overall sound level as flat as possible. Yeah. So this is like kind of jamming. Yeah. So then in that case, receiver will get the information, but it will be like all sound level is same, so he may say every bit is 0 or every bit is 1. Okay. Yeah. So we are not going in much details, but if you want, basically that's in a paper, I will tell you later on. Yeah. So now let's see like how this is exactly basically happens and how some attackers can bypass this. Okay. So remember, like we said, you take the sound label over the time and translate that into the frequency domain. Yeah. So you will find at certain frequency there is something transmitted, the sound that we cannot hear. So what the jamming will do, basically it's going to add just extra noise at the transmission frequency. Yeah. But attackers can be clever. Yeah. So we proposed some kind of anti-jamming approach, which means how an attacker can bypass this and still get the information. Yeah. So you know what attacker can do, from the transmitter side, they can have some agreement like what will be the typical frequency levels. It still cannot be heard by human, but we can keep switching. Yeah. So it's like if signal is being jammed here, it can basically after some time change the frequency at which the information is transmitted. Okay. So it can be modulating the frequency. So in place of transmitting at 18 kilohertz, you can transmit at 21 or 22 kilohertz. Yeah. So you can see like then it cannot be jammed or detected. So this is like a bit of advanced attack. Yeah. Similarly, you can think of this kind of changing the frequency of transmission in all the approach. Yeah. Even in temperature, you remember we transform the time signal into frequency, then we did some scanning, right? And then there was a frequency label. But attackers can be even more clever. They can, again, they can make some arrangements with the transmitter receiver. They can keep shifting from one to another, and then you are confused. Detection is confused like at which actual frequency really the information is being transmitted. Okay? So this one, again more details is available into this paper. Okay. Yeah. So I'm just trying to give some kind of high level idea and just telling the main principle how things are happening. Yeah. Exact details, equations and everything, they are present in the paper. Okay. Okay, any questions here? Yeah.
So like there was a method which we used to cool down the like course, the fan speed method. So for that we are like not blocking the temperature covert channel, but we are also giving the like audible sound na, that can be detected.
So audible sound, I mean, so you mean audible sound with the fan?
Yeah.
It can be, yeah.
Like
so it is interesting, yeah. So the noise level of the fan can be used, yeah.
Or we can like use the temperature channel and subtract the sound from the fan and get the signal more proper.
Yes, that's interesting, yeah. It can be done, yeah. We have not explored that, yeah. But some experiments can be done for this, yeah. Okay, good idea, yeah. Yeah, okay, good. But typically this sound covered channel happens in a way that sound level no human can hear, yeah. So I think the one we hear is like 20 hertz to 20 kilohertz, something like that, yeah. That is why you see it's like 18 kilohertz. So in inaudible sound range, so nobody hears, yeah. I think fan one would be like you can still hear, yeah, but still some attack can be performed, yeah. Okay, hope you find it interesting, yeah. There's no real information being used, but all the side informations, yeah, or side channel information to get the real information. Okay, now let's look some more additional interesting attacks. Okay, so these are not like the covert channel, yeah. So whatever has been done in my research group, I wanted to cover some of them, yeah. Okay. So one of them is called aging attack, yeah. As the name says, you make someone old as fast as possible, so that one can die, yeah. So same applies to person, yeah. So if you want to attack a person, don't give them food, yeah. They will die. I mean, they may age faster, yeah, or give them less food, something like that. So aging attack is something like that, yeah. So if I use my phone, there could be a way I make the age of my phone low, yeah. So one of the ways, I mean, okay, there could be many ways, yeah. If you are always using it too much, its age will be anyway less, yeah. But you can make even less by doing something extra, yeah. So we will look into it. So one of the aging attack, I mean, it's also called something like planned obsolescence, yeah. So obsolescence means making it obsolete, yeah, making it kind of outdated. Yeah. So again, if something ages too fast, basically it's obsolete. You can't use it anymore. Okay. So this is just another term given to basically aging attack. Okay. And what exactly planned obsolescence mean? That means things are not aging by its nature. Yeah. There is some planning. Yeah. That means to deliberately set a product to malfunction within a certain period of time. Yeah. It's like someone wants my phone just to stop working within 1 year. Okay. So there is a planning. Yeah. Like within 1 year I want to make this phone not work. Okay. So that's it called like planned obsolescence, making it obsolete with a nice planning. And how it is typically done. Okay. So let's see like from a company point of view. Yeah. Why companies want to do this and how they can do that. Yeah. So companies can release new version of products, like new version of the phone, new version of the laptop, and then they set old version products to malfunction. Yeah. If they can do that, they are planning you to basically, or they are forcing you to buy basically a new updated product. Okay. So again, you are making it age fast just to get some profit. Okay. So this is kind of one way to do an attack. It's not about getting any sensitive information. It's not kind of any denial of service. Yeah. It's just like getting some profit by doing this. Okay. Now I have a question. So quite a few consumer electronics vendors have been reported of engaging in such practice. You know, this planned obsolescence attack. So do you know any of them? Let me share that screen. Yeah, I think this one won't work. Not this one. Okay. Hopefully it will take some time. Okay, now you can see the text box. Have you heard of any companies that have tried to do that? Which means they have tried to make your phone, your laptop to age faster so that you get frustrated, it's very slow or something, and then you are forced to upgrade to a new version. So green screen is used on the smartphones. Nice example. Yeah, I mean, if someone makes your screen just green or blank, yeah, so you are forced to basically buy a new product. Yeah. Any other, but do you know which company tried that? I mean, the kind of claims that has been done, it's companies will never say it. Yeah. But there are reports. If you look, just say planned obsolescence attack by Apple. So there was a time like people felt they were upgrading their phones, and in the previous one they were doing some patches, updates, and that update will have some kind of extra program, and that one is going to use one of the components into the processor a lot. Maybe the memory is used a lot, or one of the code is used a lot. If it's used a lot, basically it ages faster. Yeah, its temperature rises, and then overall the phone becomes very, very slow. Yeah, because if things heat up, they run at lowest frequency, and then you are forced to buy a new product. Yeah. So if you will search on internet, you will find like Apple have tried this in the past. Okay, but they never claim. But if you search on internet, it is found. Okay. Similarly, if you open a company of electronics, you know how to make more money. Yeah, you kind of age the products that you sell so people can buy the new ones. Yeah. But if you're caught, your reputation is gone. Yeah, so you may lose all the money. So careful. Okay, what's happening? Okay, so how this product malfunction is done, yeah. So this can be done by crafting malicious programs, like I said, yeah, like this product updating to the new version, then adding a patch that will use a specific processing element, or this can be also done by inserting hardware backdoors in the form of hardware trojans, yeah. Again, there could be a specific component, after some time it starts using some other component too much, and then whole system becomes slow or whole system dies basically, yeah. So this can be exploited to accelerate aging of key components, okay. So a program or some extra hardware circuit, okay. And here a hotspot node is a typical target. So typically the component in the processor that is used a lot, you want to use even that more, so that it becomes slow and it ages faster and whole system is basically shut down. Now let's look at an example of network on chip aging failure, okay. So network on chip, you know, we saw this 3 by 3, right. So each of the cores are connected by a router, and then routers are connected with some links. So that thing is the router and the links, they are called network on chip, okay. So here if you look, if in this network on chip, so these are processing elements connected by the router. If one of the processing element fails, then you can shift the workload of this to something else, yeah. So there is, because there is core redundancy, so that's not a problem. But if one of the router fails, imagine now no communication can happen through it, okay. So this is more serious, so whole chip fails. So some companies may try to do that, like just making one of the centralized router fail, so whole system comes to a stop, okay. And what is manufacturer's preference to do this? So as soon as the warranty expires, they want to do it, yeah. So after that you cannot go to their warranty center, yeah, like my phone has stopped working, like warranty is done. So you prefer basically replacing to the new one, okay. So that's typically the time the vendors want to do it, and this is all towards maximizing the profit, okay. How the profit model can be developed, yeah. Now let's say there is a series of phones, yeah, like maybe Apple or Samsung, yeah. There's a lot of I series, yeah, 14, 15. So if they are coming with their ith version, that is the next version of the device, yeah, let's say iPhone 15. So what will be their profit? So it's like how much they have produced, all the quantities. So the price for each minus the cost for each, yeah, and how many they have produced, yeah. So this will be the total basically profit, okay. And this SI is basically the number of sold prices for this ith version, okay. Now if you are planning a planned obsolescence attack, you have to basically make sure the new version is sold as much as possible, yeah. So there could be some equation like that, yeah. So let's say how many new devices of the new version are sold. So there could be some new customers, yeah, that is S0 here, and there could be the previous customers like that are in maybe I-1 version, yeah. If it's I-15 is released, then who are in the 14th version, who are in the 13th version, and then what is the probability of them to change the phone, okay. So this is how companies can estimate how many of the new version device they can sell, yeah, okay. So just this is kind of a profit model we have developed, okay. Now let's look one of the aging attack algorithm that we have developed. So again, how it works, if you remember I said if you look over the time, there is a warranty time, right. So this one is like years, yeah, this is like 3 years, and if the warranty is like 2 years, so just after 2 years you want your device to age fast, so that consumers are forced to replace. So on the vertical axis, this is a value called change in the threshold voltage. Okay, so for any electronics are made of transistors, yeah. So these transistors, over the time, there is a change in the threshold voltage, and it keeps increasing. Okay, so if you are running in a normal condition, your device, yeah, so it's like it will start here, yeah, the red line, yeah. So if like after 1 year, the change in threshold voltage might be like 8, yeah. After some more time, it will keep changing. Okay, so in the normal condition, you can see reaching it to 10 might take like 3 or 4 years, yeah. And when the change in threshold voltage reaches 10, we are assuming like this is the failure threshold point. Okay, after that, the device may become very, very slow. It's kind of useless. Okay, so in a normal condition that will happen, yeah. But if you want to aggressively age this device, you can try to reach 10 as quickly as possible, right? So there's something like aggressive aging, yeah. From the very beginning, you try to use it too much, and then you will reach this change in the threshold voltage maybe just in 8 months, yeah. And after that, the device becomes useless. Okay, but what can be the nice planning? Yeah, planning could be in a way until 2 years you don't do much, yeah, you try to reach there, but just after 2 years you start it aging, yeah. In maybe in 2 years 1 month your device is gone, and then you are forced to buy it new one. Okay, so this is basically, this is how planned obsolescence is done. Okay, so reaching the failure point at the right time as soon as the warranty expires. Okay, yeah. So this is how, I mean, how this can be done in a kind of a network on chip environment. Yeah, we looked network on chip, you saw, right? So with each router we can attach an entity that can have 2 components. One is trigger, that is going to basically trigger where that router should be used more, that means accelerate, whether that should be used less, so decelerate. Okay, and this is kind of routing computation stage. Yeah, this is called like routing computation, like how the packets are going to flow. Okay, so here this one basically can be exploited to accelerate the aging just after the warranty period. Okay, similarly, like before the warranty period, companies may try to kind of decelerate so that it reaches the thresholding point just near the warranty point. Yeah, not much faster. Okay, so here, like if you want to accelerate, this is how you can do. Yeah, let's say there is a source, there is a destination, you are sending some packets. If you remember, I said there is a like a hotspot node. Yeah, that has to be used a lot. So they can route a lot of packet from this, yeah, from all the source to this. So this particular component or this particular router can fail, and then most of the chip become useless. Okay, so this is how you can accelerate. Similarly, you can decelerate, but you want to do it before the warranty period. Yeah. So here, let's see if that particular router is being used a lot. So if it is less than 2 years, you can try to use another path. Yeah, something called like XY routing. So that hotspot is not used a lot. Yeah. So this is like one way to do the aging attack in a many core system that is based on the network on chip. Yeah. Okay. So this is a question. Can you think of any other way to do the aging attack? So in the previous one, we just tried to use the hotspot node, hotspot router more and more, right? And this one is basically just setting the hotspot node as a temporary destination, so it can age faster. Can you think of anything else? Let me do that screen. Hopefully you see the screen. So any other way to do the edging attack in the context of this network on chip based processors, okay? I mean, just you can type your thoughts, yeah, don't worry if it's wrong or right, yeah. I have just thought only one, but I wanted to check if you have thought something different than the one I have thought. Increasing the power input to chip after warranty so that it may heat up fast. Interesting. I mean, that's one way, but typically you have to use the hot spot more and more, yeah. So even if you are increasing the input power, somehow you have to divert more power to this hot spot mode, yeah. So that's one way. Using very fragile routers can be, but typically when you design the system, you make it the same, right? Yeah. Lower quality of camera. Okay. I think it's all about quality, yeah. Anything that require high computation and has no and little workaround could be prone to aging. Yeah, that's true. Yeah, that's what we are doing here, right? We are sending more and more packets. Recall this hardware Trojan thing, yeah? What exactly it was doing. So hardware Trojans, like, it's related to basically the first point, yeah? You can say increase the power level, but maybe you can have a hardware Trojan in one of the routers, and when the power requests are going to the global manager, this one can always request more and more power, yeah, and it can heat it up and then can let the whole system down. Yeah, that's one way. Okay, you can hardware Trojans can be used. Okay, good. Okay, sorry, not this one. I need to go that slide. Just a second. Okay, so I mean this for this aging attack specifically, yeah. If you look this paper that is about emergent design challenges for embedded systems and paths forward. So if you look in the security section, yeah, or reliability section, you can find like how this aging attack is done, yeah. So more details are into this paper. Okay. Okay. So next one, again that has been done in my group. We are going to look in vehicle network attacks and countermeasures. Okay. So you know, like the vehicles, like the cars that we used, there is a network inside it, yeah, but that network can be attacked, and then how that attack can be stopped. So this one we are going to cover maybe after a 5 minutes break, yeah, like I said, it'd be good to relax a little bit. Okay, just 5 minutes of break, then we start. Okay, and if anyone has any questions in the meantime on the aging attack or the one previous we did lots of covert channel attacks, feel free to ask. Yeah.